All right, welcome everyone to our weekly Water, Wetlands, and Watersheds seminar. It is February 3rd, 2021. Today we are lucky enough to have with us Dr. Miles Medina, and he's going to tell us about nitrogen and red tide and harmful algal blooms. And Miles has his PhD in 2019 from UF, from the Ag and Bioengineering Department, where now not many people can say this, he developed an expertise in chaos and complex hydrological systems. So chaos and causality. I think actually a lot of PhDs are studies of chaos. It's just not on purpose. So you studied on purpose, chaos and causality. And now you are an environmental scientist and data engineer at Wood Environment and Infrastructure Solutions in Gainesville. So it's a local environmental consulting group where he focuses on developing data management and analysis tools for air and water quality, and stormwater treatment, water quality restoration all across Florida. Miles, I've known for a couple years now. It's been in my classes before, and I'm very intrigued to hear about the research that he did to finish up his PhD. So Miles, the floor is yours.
All right, let me just share my screen. Okay, is that looking good?
It's coming up. So there you go. Perfect. We got it.
All right, cool. So I appreciate the invitation. It's a real pleasure to be able to speak to you, the UF people today. Like David said, I got my PhD coming up on 2 years ago, and I've been working in a consulting firm since then. This work was part of my dissertation. The paper was published last year, and I'd be glad to share it with anyone. The title is Seasonal Dynamics of Terrestrially Sourced Nitrogen Influenced Karenia brevis blooms off Florida's southern Gulf Coast. And as the title suggests, we wanted to look at anthropogenic drivers of blooms near the shore. I want to acknowledge my co-authors, Ray Huffaker, my committee chair from ABE, Jim Jawitz from Soil and Water Science, and Rafa Munoz-Carpena, also from ABE. All right, so before I get into the study itself, let's see. I kind of want to introduce some of the, like for background, some of the ideas that contributed to this work more broadly in my dissertation. So one is this, you know, when we talk about human intervention and management in environmental systems, it's very common, I think, in modeling and in empirical work to treat human intervention as sort of a stochastic forcing process or like a pulse disturbance, this kind of thing. And I was interested in systems where humans have a really strong influence, and maybe that stochastic kind of paradigm isn't really the best fit. So the idea is that when humans are interacting intimately and persistently with a system, there's feedback, and there may be systematic things going on that we can detect using tools that are going to end up being outside of the normal realm of statistics. So, you know, the idea is basically the environment kind of influences human behavior, human interventions affect the environment, and there's this kind of interplay that is maintained over time. Another important point is that when we look at environmental data, in particular time series, you know, there's often a lot of noise. It looks unpredictable. And sometimes that's properly considered random, but there's another possibility, which is that it can also be systematic variability that arises from nonlinearity and feedback structures, and management is one example of that. So this is the part from chaos theory where, given some, you know, very unpredictable, random-looking behavior, it might be the case that it's random, but it's also possible that that's not actually what's going on. The picture on the right shows some data that we use for a different study on treatment wetlands. This is STA34 from the Everglades system in South Florida. And the point I want to make here is just that, you know, the sort of theoretical explanation for this type of system says that outlet concentrations seek equilibrium. And if they're not in equilibrium, it's probably because something from outside is sort of knocking them around and adding noise. But our study found evidence showing that management feedback in a systematic way was contributing to the observed non-equilibrium behavior. So this instability, this volatility in the movement of the outlet concentrations wasn't simply just random noise. It was actually something structural in the system in the form of management feedback. And in particular, that had to do with management making decisions about how much water to put in the wetlands, partially on the basis of what was going on at the outlet. So how much phosphorus is coming out, and then making adjustments to hydraulic loading. So this is the kind of feedback that can happen. And then the final point is, in empirical work, it's very common to look at correlations as sort of, I think, an initial screening test. Like you have a hypothesis, and if you don't see correlations between variables that you expect to be interacting, you might disregard that part of the hypothesis. But there are actually tools out there that are more subtle that can detect a situation where variables are interacting in a persistent and systematic way, despite no observable correlation. So this is very common in complex systems where the relationship isn't strictly proportional or even monotonic. The correlation might shift in direction or magnitude, and all the while these two variables are interacting consistently with each other. So this is some of the background ideas. Now to get into the red tide study itself, I'll talk about the life cycle of a Karenia brevis bloom. It initiates offshore under the right conditions, and then it can move toward the coast. And our focus is on anthropogenic influence once the bloom appears near the coast. I want to say I'm not a biologist, I'm not an algae expert, but I'll relay what I know from doing this work. Then I'll get into the methods a little bit, just to kind of give a flavor for this different way of thinking about stuff. We didn't collect any of these data ourselves. These are monitoring data from NOAA and from the South Florida Water Management District. And basically the methodology allows us to isolate hidden signals, systematic patterns of behavior, and then uncover complex relationships among variables that we're interested in. And then finally, I'll discuss the evidence linking anthropogenic nitrogen to blooms near the coast. So just a little introduction to red tide blooms. Karenia brevis is a dinoflagellate species, a marine species. It's naturally occurring. Blooms in the Gulf. Can you guys hear me all right? I'm getting a warning about unstable internet.
It's a little shaky, but we can make it out.
Okay. So these blooms are well documented for hundreds of years. They're naturally occurring. And the way they come about is you have oligotrophic conditions out in the Gulf, more or less in this area over the West Florida shelf. And there's sort of a cascade of effects that can culminate in a monospecific bloom. So you get iron deposits carried over with the Saharan dust from Africa that travels over the Atlantic. That feeds trichodesmium, a cyanobacteria that fixes nitrogen. That nitrogen fixation process is sort of leaky. So as they're fixing nitrogen, some of that inorganic nitrogen ends up in the water column. That can in turn feed the Karenia, and the bloom can sort of gain momentum and take off from there because it can utilize a variety of nutrient sources, including nutrients from fish that were killed by the Karenia's own neurotoxins called brevetoxins. And these are the same neurotoxins that can cause respiratory illness in humans with a coastal bloom. Okay, so at this point you have a bloom out here in the Gulf, and under the right sort of oceanographic or hydrodynamic conditions, an upwelling circulation pattern can emerge. The bloom can advect along the bottom Ekman layer toward the coast and then appear near the surface somewhere along the Gulf Coast. So I think this is the case with a lot of harmful algal blooms around the world. There's pretty wide recognition that anthropogenic or terrestrial nutrient sources can help maintain and contribute to the severity of these blooms near the coast of Florida. But there's actually been, surprisingly little empirical evidence to back this up. It's sort of taken for granted, but it hasn't really been clearly demonstrated as far as I could tell in the literature. A review paper from 2012 said that the idea that more nutrients means more algae is simplistic. And, this suggests recognition that this is a complex system. Whether nutrients actually have this effect on blooms can depend on other things going on in the system. It's probably something state dependent. So it shouldn't be surprising that correlations are kind of few and far between. And so this motivated us to want to investigate this a little more deeply using these tools based on chaos theory and nonlinear dynamics. Again, an important point is that a lack of correlation doesn't necessarily mean that there's no causal relationship. So the research was framed in terms of these three questions. First of all, do blooms exhibit a systematic pattern of behavior over time, what we call a signal? And the idea here is that if we can isolate a systematic pattern of behavior and identify that that exists, that would imply that there is some systematic interaction, some systematic driver, perhaps, that is interacting and contributing to the bloom. So the next question is there evidence that any anthropogenic factors, like nutrients or freshwater inputs, are systematically influencing the blooms? The focus on anthropogenic here is simply if we're making the problem worse, it'd be good to know that so that we can try to change something and not continue to do that. We're not going to stop the blooms from happening altogether, but can we stop exacerbating them if that's the case? And then the third question is, if we can identify anthropogenic drivers, can we trace that influence to particular basins in the watershed and target efforts to mitigate that effect? Okay, so this slide shows the study area and the study period. Like I said, we got data from NOAA. So all these little red dots on this map on the left show sampling locations between late 2012 and early 2018. In all, there were over 9,300 data points. These were data collected somewhere between the 26th and 27th parallels and within 10 miles of the coast. So we took these data, we aggregated them into a 2-week time series over this 5-year period. And basically that just means for each 2-week period, we took an average of all the sample data available. We also used flow data and water quality data from 3 South Florida water management control structures. That's S79, which is the discharge point of the Caloosahatchee River to the estuary. Another structure a little bit upstream is the S77. So this is the discharge point for Lake Okeechobee to the Caloosahatchee River. And then further upstream, we have the S65E structure that releases water from Kissimmee River into the lake. We also pulled some data for stage from various locations throughout the lake. And the picture on the right shows land use in the Caloosahatchee and Kissimmee River basins. So the Kissimmee Basin is really dominated by agriculture in green. You have some urban areas in orange. And then the Caloosahatchee River also has a lot of agriculture and then in the upstream part of the basin, and then also a lot of urban development down in around the estuary. Okay, so this slide sort of outlines the data analysis framework. So I think it breaks down into kind of 2 steps. The first one is signal processing and diagnostics. So this is where we try to isolate any signals that might exist in these complex time series. And here we use a method called singular spectrum analysis that I'll briefly describe on the next slide. If we obtain a signal, we can run it through some diagnostics, basically to check whether it's okay to proceed with the causality tests that follow. These tests look for nonlinear stationarity and low dimensionality in the system dynamics. And then we move on to the causality tests, which of course are there to quantify systematic causal interactions. This is where we can do like pairwise comparisons to test hypotheses about drivers. And the method here is called convergent cross mapping, or CCM. This is a really pretty new procedure. This was first published in 2012. And when it first came out, people started noticing some problems about, with false positives. It was identifying some spurious relationships. So there have been some tests for false positives that have come out. We applied a couple of these to screen out for common sources of false positive results. Okay, so a little bit more about singular spectrum analysis. If you're familiar with principal components analysis, this is very closely related. Basically, if you have a noisy, or if you have any time series, but it's particularly interesting when the time series doesn't appear to show any structure. There's a decomposition procedure, and you can look at the components and make a decision about whether they show structure or not. So in this case, let's say we decompose into 4. This is a very oversimplified example, but here we're decomposing it into 4 components. We've got 3 very clearly structured components. They just look like sine waves. And these are going to be signal components. Everything that's left is just regarded as noise. So this is like high dimensional or stochastic variability. And we can collect these signal components, add them up together, and get the total signal, which is shown in red on the right-hand side. So the signal is like an aperiodic pattern of behavior. And the complexity in the signal is just due to, like constructive and destructive interference of adding these 3 waves together. So you can get this pattern that is, not as clean looking as the components that the signal comprises. All right, so an important point here is that environmental systems behave in complex and unpredictable ways, but complexity doesn't necessarily mean randomness. Okay, now from the signal, this time series in red, we can actually learn quite a bit about how the system is structured. So it turns out that in complex systems, variables are interacting, and they actually share information by virtue of those interactions. And what that means is that when there's a lot of interactions, information about the entire system can be encoded in the dynamics of a single variable. So you can learn something about the system overall just from the data on a single variable. So this slide is really, I'll try to not get too in the weeds here, but this is really the magic behind this kind of analysis. This picture in the panel A is basically showing the trajectory of the system. You can think of it as sort of tracing out the attraction basin for this made-up system composed of 3 variables, x, y, and z. Now, this would be like complete information about the system that we don't actually have access to because we don't have information on every variable in practice. But with information on a single variable like x, we can reconstruct this geometry or topology and get what's called a shadow attractor, a shadow manifold that retains a lot of properties about the essential system dynamics that are represented graphically by this attractor. So, this picture obviously bears a resemblance. It's not identical, but the point is that it shares some essential information about the dynamics of the system, and that's recovered just from the dynamics of the one variable. And we can do that with any variable we have data on. So if we do that with multiple variables, in this case, x and y, it's sort of like looking at 2 shadows cast from the same object, but at different angles. And we can compare those shadows and make a determination about whether they are indeed cast by the same object. And if they correspond in this way, that's an indication that the 2 variables are actually interacting in the same system. They're causally interactive. So this is really the kind of intuition behind the causality test. Okay, so to get into results. So the first question about in the research was about, is there something systematic going on? So we looked at the log base 10 density of Karenia brevis, and that's the black time series here on the top left panel. And we're interested in the log transformation because we're interested in blooms, right? So we care more about the order of magnitude rather than the actual magnitude itself. And in this case, we obtained a pretty strong signal. Explains 78% of the variance in the time series. So you can see it captures, at least most of that variability. The signal had three components. In red, there's an annual cycle, which captures seasonality. There's a half-year harmonic cycle in blue. And then there's also this green trend that might be part of a slower oscillation, or it might just be a trend. And then at the bottom, we have the residual noise, the variability that was left out. So we repeated this procedure on 10 different possible drivers from the watershed. I'm showing results here for one of those, S79 NOx. That's the station right here at the mouth of the Caloosahatchee River. And here again, we found a fairly strong signal explaining 59% of the variance. There were two components, an annual cycle in red, and then that half-year harmonic in blue. So this table is directly from the paper. This shows the signal processing and diagnostic results for Karenia brevis, and then for each of the 10 candidate drivers. And in 9 of the 10, we had a very strong signal to pass the diagnostics. There was one case where we didn't get a signal. Okay, so then the question is, which among these can we find evidence for a causal relationship? Which one of these is driving the bloom dynamics? So there were 9 tests for each of the 9 signals, considering each as a possible driver. The only hit, the only positive result was S79 NOx, which I showed the signal on the previous slide. So I don't unfortunately have time to get into what these graphs exactly represent, but there are details here that give a lot of confidence that this is a solid result. Basically, one of the outputs is you get a rho, kind of a equivalent of a correlation between 0 and 1. 0.75 is pretty strong. We've got a low p-value. So that nitrate concentrations at that S79 station is identified as a driver. Here for S65E, this is that station north of the lake, near the end of the Kissimmee River. We got a negative result. Okay, the rho was high enough to be a possible hit. P-value was very large. But looking at this graph, it suggests that maybe there is actually a link there. And this might be a false negative. And this is a limitation of the study, is that we're using about 5 years of data, which for this kind of work is actually kind of a short period of record. So with more data, we might be able to clarify this result and see if this was indeed a false negative, as I suspect. But I can't say for sure right now. On the right, we have the phase-space reconstructions like I described on the other slide. So this is basically a picture of the system dynamics from the point of view of the red tide bloom signal. And you see there is some structure there. It's not just a big rat's nest. And it has this kind of shape like an ear or a bean maybe. And there's a resemblance to the reconstruction, to the S79 NOx. So it's not surprising that a causality result would show a connection there. Okay, the next question was about tracing the influence, the signal further upstream. So since we got a hit with S79 nitrogen as a driver of Karenia brevis, the next question is, well, what's influencing that? What's influencing that nitrogen? Can we find a link further upstream? So we tested data from, let's see, S77, we tested stage data from the lake, and we tested nitrogen data from S65E. We didn't get any positive results here. This one, the S65E nitrogen as a driver of S79 nitrogen, that test was negative, although the rho value was high, p-value was a little too high. But again, here we see even more indication that this might be a false negative. It has to do with the shape of the envelope of this red cloud of points here. It suggests that there might actually be something going on there. So this is something worth investigating a bit further, I think. The point being that, if we can find evidence linking nitrogen from the Kissimmee River basin to conditions at this station, S79, and ultimately to the red tide blooms. I mean, that's important management information. Okay, this table is again directly from the paper. We see all the results from all the causality tests that we performed. The only positive one was S79 nitrogen driving blooms. Everything else was a negative result. Okay, so conclusions are, first of all, the complex bloom dynamics showed temporal regularity, a strong signal, including a strong seasonal cycle. Nitrogen dynamics at the mouth of the Caloosahatchee River systematically influenced the blooms near Charlotte Harbor between 2012 and 2018. And this suggests that the duration and magnitude of blooms near the coast would be mitigated by nitrogen source and transport controls within the contributing basins. However, of course, the extent to which the mitigation efforts should be targeted at the Caloosahatchee Basin or at Lake O and discharges from the lake, or at the Kissimmee Basin remains unclear for now. So some limitations and next steps. First of all, we only looked at data from that kind of flow path, Kissimmee, Lake, and Caloosahatchee. There are other rivers that contribute to this Charlotte Harbor coastal area, so but the data weren't sufficient to include in this kind of analysis. So maybe in the future, we can look at Peace River and Miaka rivers as well. The false negative causality results, as I said, well, the negative results were possibly false due to the short study period. So I think it's going to be worth repeating the analysis now that more data are available. We're 3 years out from the end of the period of record in early 2018. So this year I plan on kind of revisiting this now that we have 3 more years of data. I also want to look more deeply into this nitrogen and Karenia brevis relationship with a tool called phenomenological models. This is kind of a system identification tool. And, you know, it's possible that under the right conditions, more nitrogen just facilitates these blooms, but it's also possible that things are a little bit more complex and there might be some ecological interactions facilitating or inhibiting that process. So that would be interesting to look at. And then finally, I also want to extend the analysis to the East Coast to investigate whether there's an effect of Lake Okeechobee discharges on blue-green algae blooms near the St. Lucie estuary. Okay, so here's some literature. This is the paper I presented, published last year. A couple of important papers on Karenia brevis in Florida, although there are many more. And then some of the sort of foundational papers for the analysis that we did. And I'd be glad to share any of these with anyone who's interested. This is my contact info. I still maintain my UF address. You can find me on LinkedIn. And thanks so much for your attention. Look forward to the discussion.
Thank you, Miles. That was great. It's a topic of interest to a lot of folks. I'll say you've got like 35 people on YouTube right now watching as well. We don't know who they are, so just be warned. And we've got, I think, a lot of questions both about sort of methods and interpretation. I jotted some of my questions down so I didn't forget them, but I would like to open it up to the room first. Anyone here on the Zoom who'd like to ask Miles a question? I'm going to start at the very top then and just really put you on the hot seat to tell us about causality, and in particular the causality that you found, if I can say it correctly. NOx at S79 was determined to cause blooms. Will you say that? That's what you found. So
yeah, I think that's a safe way to state it. Yeah.
So I guess the big question is, we can all believe the Granger cross causation mapping or whatever, but how confident are you in the sort of the true causative nature of that relationship, and what are the caveats? I mean, from what I understand about the lagging, it's about a sort of temporal relationship, whereas you could still be confused by correlation among NOx at S79 and something else like number of alien visits to Southwest Florida. If they were also perfectly correlated, you'd find that the NOx was the cause of the algae blooms, right? So can you just give us a little bit of philosophy about causation?
Yeah. So that's an important question, and it does get philosophical, and the word can mean a lot of different things in different contexts. Just to be clear, it's not these results aren't to say that nitrogen is the only cause. You know, it's well documented that these blooms occur naturally. There are a whole set of conditions that have to occur for blooms to manifest. But what these results mean is that the nitrogen is at least influencing that process. And I was very careful when choosing my words for the title because I said influence. You know, it doesn't necessarily mean, I mean, I suspect it means, but it doesn't necessarily mean that it's, you know, 100% of the time facilitating the blooms. There might be some complexity there that we're not aware of. Some conditions where the nitrogen might actually inhibit it. I mean, it's hard to think of, but it's possible. So the causality in this context, it's about systematic and persistent interaction. It's not about like pulse events. So that's why we isolate those signals to begin with. And there's always a risk of false positives with any kind of empirical work. But like I said, there are some sort of safeguards with these screens for false positives that we put in particular to avoid the kind of spurious correlations like you're talking about, where, you know, it's possible that things are sort of in phase with each other, but they really have nothing to do with each other. And there is a screening step that we use to try to knock out that possibility.
Yeah, I think it's really interesting, and I think an approach that a lot of us are interested in employing more. So we're definitely going to come find you and Ray. So here's a question from the YouTube. It's from Xuan Hu. He says, "Great talk, Miles, and thanks to you. My question is why nitrogen at S79 is a key factor, but flow at S79 isn't. Shouldn't the product of both, in other words, the flux, be more important than either one on its own?"
Yeah, that's a really good question. Every time I do this kind of work, like for the SDA study as well, that issue of using loads instead of concentrations comes up. And I think in an ideal world, that's the route we would go. But of course, loads have to be derived from flow and concentration data. And that calculation inherently has a lot of uncertainty in it because of the way the data are collected. So I tend to prefer to go with the actual observed data, which concentration is the best we have. We also did look at flow, and apart from concentration, and that didn't show a causal relationship, interestingly. But yeah, the point's well taken. I mean, that's definitely, load is certainly important. And I guess the hope is that concentration is a good proxy for that.
I guess it depends on the periodic signal of the flow, as well, which should be pretty strong. I think that certainly is interesting. If you have low flow and high concentration, you can't, presumably from an ecological point of view, fuel as large a bloom when it comes down to just the metabolism, productivity of a community. So Kathy, you go ahead.
This is a very interesting analysis. Can you identify a parameter or a set of parameters that should be monitored based on the analysis?
Yeah. So I have to admit to a little bit of an oversight on my part. You might have noticed we only looked at NOx concentrations. And at the time, it didn't occur to me to add together NOx and TKN to get total nitrogen. There was a shift in the way that the South Florida Water Management District was reporting their nitrogen sampling nitrogen. And so at first it seemed like they hadn't sampled total nitrogen for very long. And then looking at it again, I realized, oh, I could have just added these things together and I should have done that. So that's something I want to check out as well. It does seem like the data are there for the stations that are currently collected. So that's another important avenue and a limitation to this study. In terms of adding, additional data, and collection, I mean, the higher spatial resolution and temporal resolution that data are collected at, the better. So to really get targeted into subbasins and so on, I mean, it would be helpful to have data from throughout the subbasins. But, I think we can still learn quite a bit, at least on the basin scale, Caloosahatchee versus Kissimmee and so on, with the data that are there.
Thanks. And just following up on that, Christine Angelini also asked, she really appreciates the important and great work. And so more data is always better. Are there any particular variables? I know more resolution is better, but are there, wind speed, the phosphorus, phase of the moon, whatever, aliens. Yeah, the thing, what else would you like to add to this model to make it, that might be fundamental to the process?
Yeah, so the phosphorus data are good. Hey, Christine, it's good to hear from you. I think something Christine would be interested in as well would be more, biological data there in the estuary. So I would love to look at ecological interactions, with other species that might be facilitating or inhibiting these blooms. And I haven't looked into it, very deeply. I don't think there's a ton of long-term species abundance data on different kinds of algae out there, but I could be wrong. But I'd love to talk about that more. Yeah.
All right, well, I'll ask you a technical one, and anyone else online, feel free to just pop in a question into the chat. So when you do the signal decomposition, it's like in signal processing, right? You have different wavelengths, you got maybe shifts, they don't have to have the same start time. So they can make really complex looking shapes, but they are periodic, right? Like at the longest time scale, when you add them all together, you get a repeated pattern, right?
Yeah, so each component, what really distinguishes it as a signal component is that there's a peak in the Fourier spectrum. So there's a single frequency, sometimes two frequencies, but you want to see basically some form of sine wave, and the amplitude might change over time. The phases are can certainly vary among components, but yeah, basically the components are these nice, clean looking oscillations. And
so that means that like for the longest time, like the lowest frequency, the longest time scale, well, you would need at least one, but one seems like a little dicey. Like, do you, in spatial autocorrelation, you want like 10 of the biggest autocorrelation lengths. And if your largest pattern is like a 50-year cycle, so can you tell us a little bit of just about like care in interpreting especially, what do you call it, low frequency, whatever, the very long ones?
Yeah, totally. So that was, that's exactly one of the limitations here, is we were really kind of pushing it with this 5-year period of record, which was the Karenia record was the limiting factor, because right, to see something as a pattern, you have to see it repeat, right? So if it's easy to distinguish an annual cycle, you have 10 years, 20 years of data, but if you have a 20-year cycle and you have 25 years of data, that's just going to look like one up and one down. And is that a trend, or is that part of an oscillation? And that's never really clear. You are limited by that time window and what you can actually distinguish as an oscillatory component.
But you were able to fit, like, one of those very long ones was a long period of a low frequency signal, even though you had only a portion of it. And so, right, you have to kind of go on faith in the interpretation that the part that you're capturing wasn't a trend but was a cycle.
Yeah, I mean, it's okay to include some trends. This takes a little bit of judgment, and I think different practitioners might make different decisions. My criteria are usually, if I have a component like that where I'm not really sure it might be on the line, whether to include it or not, that's where I lean on those diagnostics. So if I run it through the diagnostics and it gets through, then I say, okay, it's a trend, but it's not such a huge deal that I should knock it out, because it's really changing what we can consider systematic. In this case, it did pass the diagnostics, so it's okay. What can happen with a trend is when you're looking at those phase diagrams, it will cause like this kind of drift and spreading of that manifold. And that can really just get in the way of the causality analysis, because these attractors are supposed to be like compact and sort of aperiodically orbit around the same basin. So, trends are definitely something that you have to watch out for. And a lot of times we do exclude them. I don't recall exactly, but there probably were some that we didn't include here for those reasons. But yeah, there are sort of edge cases where is it signal or is it noise? Is it, and that's some of the art of the signal processing.
Thanks. We have a question from Eric Milbrand from the Sanibel Captiva Conservation Foundation. He asks, could you derive some pre or post-bloom indicators by including high frequency salinity or chlorophyll data from the area between S79 and the Gulf?
Yeah, so okay, so that's an interesting question. I mean, all of this work is strictly inferential. This really doesn't have any predictive value. This is all like just looking in retrospect. There are some tools out there, and I haven't worked on this in a while, but last year I was working on a prediction model that's got its basis in this kind of phase space paradigm. And yeah, it's possible. There's a tool out there called randomly distributed embedding that sort of Monte Carlos through a bunch of different phase space reconstructions. And you can toss in a bunch of different variables that might be useful in prediction, and it will use the ones that are the most useful and then come up with predictions. It's a little tricky because it seems like the predictions tend to lag a little bit. And so that's not very useful, because if you want to predict that a spike is about to occur, you want to know now, not right after it occurred. But yeah, it's possible within this paradigm. I mean, that is something I'm interested in. I just haven't had the time to pick it up again for a while.
Thanks. I know Eric is, he's interested. He's down there, and if he was able to, he has a nice monitoring setup, and if he was able to get an early warning ping, that would be really helpful. I guess one thing that's interesting that is all of this inferential work is on the mean aerial averaged, 2-week temporal average bloom, or concentrations, basically, right? Like biomass or abundance or something. Yeah. And none of the predictions ask anything or know anything about the state of the loop current or the direction of onshore winds, and all this stuff. So you can reconstruct that periodicity, which seems to suggest that there's like bloom formation and onshore advection that's like super predictable, which maybe seems too simple. So can you tell us a little bit about that?
Yeah, I mean, I think that's an important question. Like the prediction thing I was just describing, I'm not sure. Like it could be really powerful, but I could also see it sort of missing things like you're saying. I mean, there's a lot of physical processes that go into this, and maybe the best predictive model is going to be a mechanistic model, not something empirical. And it's hard to say without trying. If you want to predict events with accuracy. So yeah, that's sort of a different realm, the prediction, and honestly, it's one I'm less familiar with, less engaged in.
Yeah, Miles, I was just going to ask a quick follow-up, kind of what David just hit on. It was a great presentation. I'm still wrapping my mind around the deconstruction process and trying to move to actual causation versus just correlation, but I got work on that to do. But with regards to that response side, which is the Karenia brevis bloom, is it and these other factors that might be happening actually once it gets out into the nearshore environment, is that where you think most of that residual is coming from that you can't explain through these other sources? Or if you were to isolate a particular station and look at its response that might be in a closer proximity or something like that, do you think your predictive capacity or your correlative capacity would go up? Or I'm kind of curious where you think some of this residual error might be coming from.
Yeah, so in general, environmental data are noisy. There's going to be, sampling error. Like David said, this is kind of a spatial and temporal aggregate, or Karenia time series. So, there's going to just be variability inherent in that. And then you might have just, what could be considered stochastic effects. Any physical process that might change what, add on to the variability that it's more structured. So, that's harder to tease out, and that's more of a question for like a statistical analysis or a extreme values kind of analysis. And you can kind of supplement this work with that to look at the noise probabilistically. the causes of it, I mean, that's the question, right? But typically, yeah, you've got process error and you've got measurement error, and it falls into one of those two buckets. I think, looking at the signal, I mean, in a lot of cases, the peaks line up, but it doesn't quite capture the magnitude. And that's important because, a bloom that's 2 or 3 orders of magnitude greater than what is considered deterministic or systematic is, in effect, is an important difference. And, this study is really limited to talking about systematic effects of the nitrogen. And so I guess you could make an argument that the nitrogen isn't accounting for the entire magnitude of the bloom, but it would seem that it's certainly an important part of it, So I don't know if that.
Yeah, no, that's good. Yeah, thank you.
Yeah, I mean, especially if you've got periodicity, and then your residuals are the noise that you can't deal with, and so it's not structured, at least within the set of data that you have.
Mm-hmm.
Hand that to someone else, and they can do a whole nother. I mean, presumably there's not enough structure in there, or else you would have found it. But build another statistical or even mechanistic model about the deviation. So it's like, particularly going from log 3 to 4 to 5 is a small space on the graph, but it's a large change in the number of dead fish, right? So like this is the critical element. We have one time.
Effects and human public health,
Right.
Yeah, difference.
So we got time for one last question from Anastasia in the class. She asks, can you tell us about like the seasonal impact of the blooms and like what scale sort of seasonality comes into play? And also, I guess in the river and out of in the estuary versus the river, how seasonality comes out in the data?
Yeah, so the seasonal effects were large. They were the major components of both the Karenia and the S79 NOx signals. And you can't see my screen, can you? But I can pull up the slide here. So just give a quick view of this. You see this is a case where the Karenia, the amplitude of the seasonal component is increasing over the period. And then it's kind of the opposite. There seems to be a little bit of a decrease in the seasonal component. Those are the red components in each of the plots. So, how that translates to the causality analysis is when you're looking at these squiggles here, these phase diagrams, generally like a larger amplitude is going to mean like a larger orbit, a larger radius, right? And you see some variability. You see some lower amplitude and some higher amplitude in both cases. And those corresponded in a way that, the causality test determined was basically, the two geometries or topologies here were close enough to suggest the causal link. So, that's why the title really emphasizes the seasonal effect, because that was really the main component. And then we have this half-year cycle too, which is common in signal processing. You get these kind of harmonics. It doesn't necessarily have an easy physical interpretation, but the 26-week cycle, that's a half-year cycle. So that's related to the annual cycle, which is the seasonal cycle. And that's a common thing where you have kind of even multiples of the frequencies or the wavelengths in different components.
All right, Miles. Well, I do want to put you on the spot one more time. When you started, you quoted the paper from, I think it was Anderson 2012, and said, more nutrients and more algae, it's not always so simple, or something like that.
Yeah.
So what do you think now?
I think that's still an open question. I mean, that's why I want to get into that phenomenological modeling to get at the interaction regimes, right? So it's possible that in this case, it is that simple, but it's also possible that it's a lot more complicated. And the way the phenomenological modeling works is you can put in time series data, and if it was a physics problem, it would give you governing equations that you can kind of reverse engineer the differential equations that can generate the time series. And once you have those differential equations, you can take partial derivatives variables in terms of each other, and that will tell you about the interactions. So in an ecological context, it's like, is it symbiotic? Is it competitive? Does it change over time? Often you see a positive relationship and then a negative. So yeah, I think that would be an interesting thing to look into and really get at that. In this particular case, is it more nutrients means more algae, or is the story a little deeper?
Yeah, well, it seems at least somewhat. The answer is somewhat connected, right? So we really appreciate it. Let's give Dr. Medina a round of applause, either in real life or in Zoom emojis. We really appreciate you coming to talk with us today, Miles. Great to see you. And I can guarantee that we will be in touch because this topic is very much on our mind. Thanks everyone for coming. Next week, we will be hearing from, who can get to the seminar for next week first? See if Charlene beats me. Seminar and
Don Berenger.
Don Berenger. So he's going to be talking about lobsters or something. We've got, we've got Karen Gadan next week on February 10th. Ghosts of the Coast, Ecological Investigations of a Mid-Atlantic Ghost Forest. So bring your spooky costumes, and we will see you next week on Wednesday. Thanks, everyone. Good to see you. See you, Miles. Thanks a lot.
All right. Thank you. It's a pleasure.